Hello everyone, we are going to present high-resolution radar dataset for semi-supervised learning of dynamic objects. Camera, radar, and lidar are three main sensors that are widely used in automotive industry for perception, and between these, radar and lidar are active range sensors. However, radar is much cheaper to manufacture, and is also more robust under different lighting and adverse weather conditions. Currently available automotive radars output a sparse point clouds with very low angular resolution. Such output lacks semantic information of the environment, and it limits the performance of the radar perception algorithms. Here you can see the same scene from camera, bird's eye view of lidar, and bird's eye view of the traditional radar point cloud. Now if you compare lidar to the radar point cloud, you can see the radar point cloud is much sparser comparing to the lidar, which means this kind of sparse representation becomes the bottleneck of radar perception pipeline. Low resolution and sparse radar output is mainly due to the limited size of the real antenna array. In order to move away from the sparse representation and be able to produce high resolution radar images, we can use synthetic aperture radar, or SAR. SAR is a set of related techniques for coherently combining radar returns from a moving radar over a subsegment of the radar's path. SAR has been commonly used for aerial surveillance and remote sensing. However, to the best of our knowledge, we are the first to produce high-quality street-level SAR dataset consisting of complex urban imagery. In the bottom right, you can see the SAR image of the same scene. As you can see, it is dense and contains rich semantic information of the scene to be utilized by radar perception algorithms. SAR approach requires accurate relative distance measurement between the radar and the object. For stationary objects, all we need to measure is the vehicle in motion, and this can be achieved using the GPS IMU system available on the car. However, for the dynamic objects, it's more challenging. We need to be able to first detect them and estimate their velocity. And this can be achieved using the raw radar data. This is our framework for semi-supervised learning of dynamic objects. First, we transform the raw radar data to range Doppler direction of arrival representation. Then we detect points on the range Doppler map and project those points to the SAR image. We assume that SAR image cleanly images the static elements of the scene. Therefore, dynamic points are likely to be projected to the lowest NR regions of the SAR image. Left image is the range Doppler map. Colored points on top of this map are detected points. Red refers to dynamic objects, and green points are coming from the stationary objects. Now if you look at the right image, it's the SAR image with the lidar overlay. Yellow lines on top of the SAR are coming from the lidar. And as you can see, the projected red points, which refer to the moving object, usually lie on top of the lowest NR region of the SAR. Now this is a simple heuristic to be able to classify moving and stationary points. We can combine the unsupervised labels with accurate annotations to train a deep CNN. The input to the CNN is a sequence of range Doppler maps over time to be able to utilize temporal information, and the output of the CNN is dynamic object masks. This is our test results measured with average precision over different ranges. Near range is 0 to 15 meters, mid-range is 15 to 30 meters, and far is beyond 30 meters. CFAR is an adaptive thresholding method to detect points over the range Doppler map. We have trained the CNN with human annotations, and semi-supervised CNN is first trained with unsupervised labels and then fine-tuned with human labels. Moving from CFAR to semi-supervised CNN, you can see a consistent boost across different ranges. We show the results of detecting moving objects over the range Doppler map and then projecting them into the SAR. An alternative approach would be to first generate a range-azimuth image from the raw radar data and then combine it with the SAR. This video shows the result of combining SAR with range-azimuth image, which contains both stationary and moving objects. The benefit of such representation is that you can easily train your favorite object detector to be able to predict both moving and stationary objects in the same space. Thank you for your attention.